Okay, so let's take a step back and recall the definitions and examples about the random variables from your basic probability course. So remember the examples. For example, the number of customers coming into a bank, well, the income of a, let's say, of an engineer, or the number of eggs laid by chickens in a farm, the number of accidents, or let's say the inter-arrival times of customers again coming into a bank. And remember, in all of the random variable examples, remember the examples, for example, the binomial or hypergeometric, or I don't know, normal, exponential, and so on and so forth. Okay, so we will talk about this not in this video, but in the next one, in the following one. So again, there are two important measures for the random variables, right? First one is mu, the mean of the random variable, which is denoted by ex, expected value of x. And the other one is the sigma square, the variance, okay? That's the expected value of x minus mu squared, right? So this is the center, this was the center of the data, and this is, well, how the data is scattered around the center. You see x minus mu. As you may recognize, this is very similar to x minus, sorry, not x minus mu, but x minus x bar, right, square. So this is x minus mu, and this is x minus x bar, okay? So okay, and this is the mean and this is the variance. But okay, so what is the difference between them? So we also have x bar, and we said that, well, this is mean, this is the sample mean, which was calculated by, remember, xi divided by n, and we have not a square but s square, not sigma square but s square, so which is xi, very similar, minus x bar squared, okay, divided by not n but very similar, n minus 1. So this is sigma, this is mu, and this is x bar s squared. So what are the difference between them? Because remember, for mu, well, we say that the expected value of x is equal to x times f of x dx if there is a continuous random variable. And if it's a discrete random variable, then that's x times f of x. Remember f of x? F of x was the probability mass function, and this is the probability distribution function. Okay? So for example, if we are talking about a die, remember die, so what is the expected value of the die that shows up? Okay? So it was, remember, so you may have 1 with probability 1 over 6. You may have 2 with probability 1 over 6. You may have 3 with 1 over 6. You have 6 with 1 over 6. Okay? And the expected value is 1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6 and which is equal to 3.5. This was the expected value of the number that shows up when you toss a die, okay? And similarly, this is the variance formula for the random variable when it's continuous. And this is the variance formula for what? For the variable, for a discrete random variable. And this is the counterpart of the mean for what? For the sample, okay? This is the sample mean, and this is the sample what? This is the sample variance. But this is what? These are the variance of what? This is the population, let's say. This is the random variable, the variance of the random variable, and this is the expected value of the random variable. So what are the similarities and differences between them? So there are two means and two variances. Well, in fact, they are very similar to each other. In fact, they are the same. So what do we mean by they're same? So remember, I said that please note the calculation that we did. I said that we will remember this later. So remember, when we are calculating this averages, we said that you can just do this, okay, do this and divide it by 10. Remember, so this is a frequency table, okay, frequency table. And we are trying to find the average of this frequency table. And we said that you can just multiply them and then divide it by 10, or you can just write the ratios or the PIs, the proportions. And you can say this is 0 0.1, 0 0.2, 0 0.4, 0 0.2, and this is 0 0.1. And you can calculate by multiplying this and this plus this and this plus this and this and find the same result, okay? And similarly, remember this is the this is the sample variance that they have calculated, okay, um, from a similar data, not the same but similar data, right? Remember we said xi minus x bar, and we squared them and then multiply it with the frequency that we have here, okay? And sum them up and divide it by n minus 1, or you can do a very similar thing, but what? With what? You can just do it by ni divided by not n but with 9, and multiply each of the square difference with what? With ni minus divided by 9. Okay. So let's think about a die example. Let's think about a die example. So, so assume I roll a die, let's say 120 times. 120 times I rolled a die. And it turns out that 1, 2, 3, 4, 5, 6. And let's say this is xi, and I have ni here. Let's say this is 20. Let's say this is 25. Let's say this is 15. Another 20 here. Let's say this is 18, and this is 22. Okay. So now I will find the expected value. I will find the x bar with the value that we have defined as before. So I will say pi here. So pi will be what? This is 20, right? So total you have 120. So pi is 20 divided by 120, which is equal to 1 over 6. Okay? And this is 25 over 120. This is 15 divided by 120. This is 20 divided by 120. 18 divided by 120. 20 divided by 120. Okay? So what I will do is I will just calculate x bar using this. 1 times 1 over 6 plus 2 times 25 over 120 plus 3 times 15 divided by 120 plus 4 times 20 divided by 120. I know you get bored, but 5 times 20 plus 6 times 22 divided by 120. Okay, I don't know the result, but it's something very similar to 3.5. Let's say this is almost equal to 3.6. I'm not sure about the answer, but it's something around. Okay, now please just think what happens if you do this not 120 times, but it do it with too many times, or let's say infinitely many times. Then what will be the pi? What will be the pi? Let's say infinitely many times. Okay, so let me erase this part. Then what will be the pi? Well, pi will be what? Pi will be almost, not almost, but pi on when you just do it infinitely many will be equal to 1 over 6, right? So this will be equal to 1 over 6. This will be equal to 1 over 6, 1 over 6, 1 over 6, and 1 over 6. So how do we find the expected, how do we find the x bar then? Okay, how do we find the x bar of this, let's say, of this data? Then you have x bar is equal to 1 times 1 over 6, okay? So this is plus 2 times 1 over 6 plus that, which is equal to 3.5. Okay. So, well, what is 1 over 6 and 1 over 6 here? Well, they are the probabilities, right? They are the probabilities, which is f of xi. So what is this equal to? This is equal to xi times f of xi. Okay. Okay, so that's great, right? Why? Because what we do is, well, finding x bar of a sample, if you just apply this finding x bar of a sample to a sample where you have infinitely many observations, then you see that, well, this formula is equal to what? This formula is equal to the mu or expected value formula of a random variable. Okay? So in fact, a random variable, uh, knowing the distribution of a random variable means that, well, somehow you collected infinitely many data from an, let's say, for an experiment, and in fact, you know the ratios, okay, the ratios without making an experiment, right? So in order to visualize the data, or in order to understand the data, what we do is we just collect data and write a frequency table or group data table. But if you know the random variable, if you know that the data comes from a known random variable, then you don't need this, because you know all of the probabilities associated with all of the values. Okay? So in fact, in this formulas, in this formula as well, the expected value formula is nothing but the the x bar formula where n goes to infinity. Okay. Similarly, you can show that, well, this variance of x formula is nothing but the same thing of s squared where n goes to infinity. Okay.